And we are moving to our last talk, Nobuchika Okada, talking about gauged U1 extended standard model and long-lived new particle searches.
Okay, Okay. Well, thank you very much and for invitation to speak about my recent work with these collaborators about the long-lived particles. Well, it was very unfortunate that I missed my first chance to visit Moscow last year, unfortunately. So, well, the situation is getting better. Okay, so the first, let me begin this way. Okay, so let me begin with the status of the standard model and the new physics, new particle search. As you know, the standard model, we have this is still the best theory in particle physics. But we know, and for many years, and we know we need the new physics beyond the standard model, and to supplement the many missing pieces in the standard model, and like the neutrino mass and the flavor mixing origin, or the dark matter candidate, or region to explain the origin of electric symmetry breaking, and to supplement the inflaton to derive the inflation. Well, Higgs boson can be the candidate. Anyway, so the new physics, we need a new physics. So this is status of the new physics searches, and especially I talk about the LHC search and the LHC search. Unfortunately, and actually we don't have we know something must be out there, but we know we have no evidence, no comparing evidence, and of the new particle production at LHC. And we may interpret this result in the following way, and probably there might be, and it might be the reason that the new particles is the standard model singlet and very weakly coupled to the standard model. So this is the reason why, and we fail so far, and we don't have any comparing evidence of new particle production. All right, so if this is the case, we may consider another direction to find the new physics. And one way is we may consider that new physics, we expect the new particle is weakly coupled to the standard model. So the sum of new particle becomes long-lived. Okay. So in this talk, I will discuss the new physics model with long-lived particles and discuss the prospect of discovering such long-lived particles in the future. Okay. So I need to specify the model in the new physics model first. Here I already said that the new particle might be the standard model singlet. In this case, and for the communication between the new particles and the standard model particles, I need some new interaction. We have the variety of possibilities. Here I focus on the so-called gauged U1 extended standard model. That's the standard model extension with the new force, the U1 gauge interaction. Okay. Very well-known example is the gauged U1 B minus L extended model. B minus L is the baryon number minus lepton number. And so this global symmetry is already in the standard model as an accidental global symmetry. And this model and the gauged B minus L model and this B minus L global symmetry is gauged. Well, we may justify this direction in the following way. Just thinking of this way, okay. And before in the particle physics history, before the construction of the standard model, and people discussed in the global SU2, the isospin SU2, and the U1 hypercharge as a global symmetry to classify the particles, especially hadrons, right? So after that, and actually these global symmetries are promoted to the gauge symmetry in the construction of the standard model. So in the same way that we may think maybe and gauging the B minus L and that global symmetry in the standard model will be natural. Anyway, and today I discussed the U1 gauge the extension of the standard model. The classic example, well-known example is the minimal gauge the B minus extension of the standard model. So that gauge they are based on the gauge group, the standard model gauge group, and the U1 B minus L gauge group. Okay, so this model includes the 3 right-handed neutrinos and the new particles, and also the other and the B minus L Higgs field, and to break the B minus L gauge symmetry. All right. So these are properties of the gauge B minus extended standard model. So this is very well motivated the new physics model, and that's the B minus L is already there in the standard model as a global symmetry that we can easily gauge it. And then we add the 3 right-handed neutrinos to cancel whole anomaly. So, and the B minus L gauge symmetry is broken by the Higgs mechanism spontaneously broken at the same time, and we get the right-handed neutrino Majorana masses. And after the electroweak symmetry breaking, we automatically have the so-called seesaw mechanism and to generate the neutrino and to explain the tiny neutrino mass naturally. So that's the seesaw formula. And we have this interaction, the Dirac interactions, and the MOR, the right-handed neutrino, heavy right-handed neutrino mass is generated by the B-cell symmetry break. And then we get the very small neutrino mass by the seesaw mechanism. All right. So also today I generalized this B-cell model. The generalization is quite simple, and just the B-cell model case is just a B-cell charge, but then instead, and we can generalize the charge assignment for particles. And the charge assignment is simple, just the U1 charge and the U1 charge, a linear combination U1 charge and the B-cell charge. And this is a generalization. And the XH is the free parameter and the real parameter. If you take the XH0 is a B-cell symmetric model case. And this is just generalization. And of course, the normally structure, the physics are mainly the same as the B-cell. But we have the new parameter XH. Okay, so this is the U1, the general U1 extended standard model I focus on in my talk. Okay, so here I'm going to discuss the new particle, the new long-lived particle possibility in the context of U1 extended standard model. All right, and we have the three. All the new particles can be long-lived depending on the parameter choice. And the first one is the light-handed neutrino. This is the new particles, or in the mass eigenstate, we call it heavy neutrino. Or another choice, some parameter choice, and the U1 gauge boson, we call it the Z prime boson, and they can be long-lived. And also another case and another parameter choice, and the U1 Higgs boson can be long-lived. Okay, so I'm going to discuss the search for these long-lived particle LLPs at the future experiment. Especially my time is limited, and I focus on just examples in the Tuscaloosa experiment and the FASER experiment. All right, so let me give you a brief review on these experiments. Probably you all know this, and the Methuselah, the basic idea is that this is the LHC site, and we have the LHC, the collisions, and the Atlas was CMS, and the collision point here. Then we put the detector far away, actually 100 meters away from the collision point. On the ground, in this case, there's some new particles, and the long-lived and charge-neutral particle produced. And the particle can propagate because interaction is so weak and charge neutral, and then arrive at the detector to decay, and then we have the very long displaced vortex signature. This is the idea, the main idea of the Methuselah experiment. Yeah, similar idea is similar idea. This is a new experiment FASER, and this forward search experiment. And this recently the approved experiment, and to look for the long-lived charge-neutral particles at, again, the LHC site. So FASER detector, and will be installed the tunnel near the Atlas detector. This is the Atlas detector interaction point. Along the beam line, the downstream of the beam, the collision point, the 400 meters away, and we put project and push the FASER detector here. So that some particles here produced, and the charge neutral and the long-lived particle can propagate this direction. Especially this target particle is a light particle because that produced from the many hadrons produced boosting to the forward direction. So just the similar idea, but just the mass range of the target particle is different. All right. Okay. So now, and this is the possible and future project and the future plan for the experimental plan to detect the long-lived particle. So let me discuss here and and the new particle in the context of U1 extended standard model. First topic is the long-lived right-handed neutrino. So there's some parameter choice. This particle can be long-lived. All right. So here the U1 extended standard model has the seesaw mechanism automatically. This is the seesaw formula. The light neutrino mass is expressed in terms of the Dirac type mass matrix and light-handed Majorana neutrino mass matrix. So we can use the general parameterization according to the Casas-Ibarra, and we can express by using the seesaw formula and also the oscillation data, and we express the Dirac mass matrix in this form. And this is the neutrino mixing matrix, and this is the neutrino, light neutrino mass eigenvalue matrix. And also the O is actually the general orthogonal matrix. That's how they include many include the free parameters. And this is generally also the general also orthogonal matrix. And the Mn is a heavy neutrino mass eigenvalue. So in this way, and by using these quantities, and we can express and in a mass eigenstate the heavy neutrino interaction with the standard model gauge the gauge bosons. Okay. So that we can discuss the lifetime, calculate the lifetime of the heavy neutrino. Okay, so this case in all the heavy neutrino decay mode, for example, through the W boson, the Z bosons, and the final state three leptons or quark QQ bar plus lepton, and this vortex is the induced by the seesaw mechanism. So expressed in terms of the neutrino oscillation data, right? So actually, in this work, and with aluminum dust and blue powder, and we did the parameter scan, performed the parameter scan, and to evaluate, to calculate the long-lived, to calculate the lifetime or decay length of heavy neutrinos. And this is just a parameter choice here that we did the parameter scan, and this is the maximum. This is along this line. This is the maximum value of the decay length of the heavy neutrino for the normal hierarchy case, and this is the inverted hierarchy case. In both cases, you can see, and some choice of this is the horizontal axis is the lightest neutrino mass eigenvalues. In the parameter scan, we found that, and we found that the maximum decay length of heavy neutrinos are controlled by the lightest neutrino mass and the mass of this particle itself. Okay, so we have the correlation. You can see that the suitable choice of the suitable value of the lightest neutrino mass eigenvalue and the decay length is suitable for the Methuselah detection of this particle. Okay, so this model U1 extended model, the production of the heavy neutrino is mainly done by the Z prime boson production first. Then the D prime boson decays to the heavy neutrino. That's the way to produce this particle. Okay. So this is the long-lived, the light-handed neutrino case. And I want to discuss another case, the long-lived, the light D prime boson and case. And so I want to discuss this in the context of so-called Z prime portal dark matter in the U1 extended standard model. So that's just some more the extension of the U1 extended standard model. So the U1 extended standard model, as we have discussed, and this is very simple, the well motivated is the beyond the standard model to explain the neutrino mass generation, okay, and the seesaw mechanism, to incorporate the seesaw mechanism. However, the dark matter candidate is still missing, right? So then we can consider a simple way to supplement the model with a dark matter candidate. So this case, the simple case, and we introduced the dark matter candidate, which has the U1 charge. In this case, this part, but the standard model neutral. Okay. So this case and this particle and this type of the dark matter scenario is so-called Z prime portal dark matter scenarios. They are discussed by many people. Right. So the basic idea is that the dark matter chi is a dark matter candidate. Here I consider the fermions. Right, he has here the charge under Z prime, under U1, so that it has the coupling with the Z prime. And the standard model particles also has the coupling with the Z prime, so that we have the communication between the dark models and the standard model particle. Here I consider the long-lived Z prime boson. In this case, and the Z prime boson is actually light, and the gauge coupling is very small. Okay, so this is the case I consider here. So this case we can discuss the complementarity between the Z prime boson search at the FASER experiment and the Z prime portal dark matter scenario. Okay, so we combine the dark matter scenario. We can discuss the complementarity. And in this case, the Z prime boson is long-lived. That means the light and the gauge interaction is small. So that means the interaction and the interaction of the dark matter particle with the standard model particle is really weak. So that means the dark matter is not a WIMP and have never been in thermal equilibrium. So in this way, the freeze in this case, and we consider so-called freeze in dark matter scenario. Right? So to calculate the dark matter radical densities, we always solve the Boltzmann equation. That's a usual form. But in this case, it is actually a solution it's easy to find a solution in this case. Because of the originally and the very early universe and the population of dark matter is negligibly small because this particle is very weakly coupled to the standard model particle and has never been in the thermal equilibrium. However, and the standard model thermal plasma can create this particle, even this interaction is so weak, but they can create. So the population, we get the population of the dark matter is growing this way. And at some point, the production stopped because of the temperature becomes the dark matter mass, and below the temperature below the dark matter mass, and it's kinematically impossible to produce this particle. So then we have the yield of the dark matter becomes constant. All right, so in this way, we can estimate the density of the dark matter. So here, then we introduced a very simple scenario to incorporate the dark matter candidate in the model, and that is just Dirac fermion dark models. And the model is like this. So just I introduced the Dirac fermions and the Dirac fermion left and right, and so this is we don't care the anomalies. Okay. So, but the assigned U1 charge of the dark matter to be Q. Q is arbitrary, and if the Q is not plus minus 1, not plus minus 3, actually we cannot write down the coupling with the single dark matter candidate, single new particle zeta with the standard model particles. And just taking the Q arbitrarily, actually this dark matter, this Dirac fermion is stable. So this is a Dirac fermion D prime portal Dirac fermion dark matter scenario. Okay, so I said to discuss the long-lived D prime bosons, and I take the mass relations, and the D prime is very light. Okay, so this case and the dark matter coupling with the standard model, the communication between the dark matter and standard model is just like this way, and zeta is the dark matter particle with charge Q. GB minus L is the B minus L coupling. We can extend this to the U1X case, but the simple case is I'm talking about the B minus L theory, okay, minimal B minus L theory, and then introducing the dark matter Dirac fermion dark matter candidate with the charge Q. All right, so and this is the interaction vortex, and the D prime vortex with the standard model fermion is just the B minus L charge times the gauge coupling. So then by considering this process and to produce a dark matter pair from the thermal plasma, from the standard model pair annihilation in the standard model thermal plasma, and we solve the Boltzmann equation. After solving the Boltzmann equation, this is the rough estimate, and actually the final result and the dark matter relative density is independent of the dark matter mass. And so everything is determined by the just product of the charge of the dark matter, B minus L charge of the dark matter, and the gauge coupling squared. And so if this product is around the 10 to minus 11, actually we have that we can reproduce the observed dark matter relative density. So this is the D prime portal and freeze in dark matter scenario. Okay, so then now we combine our result with the phasor and the phasor search of the long-lived D prime boson. And the phasor collaborations already figured out the search reach of the phasor experiment, and plus the other experiments for the long-lived B minus L gauge boson search. In the plane of the gauge coupling and also D prime boson mass in the B minus L model, minimal B minus L model. So, and this shaded region is already excluded by the current experiment, and the phasor 1 and at the LHC 1,3, and the search reach is around here. And the high luminosity LHC, the goal, the search reach is shaded, yellow shaded region. All right. So this region is the searched in the future and the very near future, and the high luminosity LHC we can search this parameter region. At the same time, also we have the other experiments like the proposed LDMX experiment or SIP experiment, also the Bell 2 experiment also searching for and can search for this long-lived D prime boson in the future. And so now the horizontal line, once we fix in this dark matter scenario, once we fix the dark matter charge, actually along this line, so for example, the charge is fixed to be almost 1, and this is almost B minus L, the charge is almost 1, in this case, along this line, and the dark matter relative density of the omega h square 0.12 is reproduced. So you can see that the overlapping here. This is a dark matter analysis line, and this is overlapping with the FASER 2 such region. And so we can figure this out. We can explore this region in the future. If you take the different value of the dark matter charge, and this line is along this line for this choice of dark matter charge, along this line, the omega is square 0.12 is reproduced. Now this will be covered, since this region is covered by the future Bell 2 experiment. Well, we can consider the current experimental constraint on the from the xenon 1 tone and the direct detection observations mediated by Z prime boson. Then this region, if we take the most severe bound, like the most severe case, the dark matter mass to be fixed is fixed to be the 30 GeV, and this region is already excluded. Anyway, we can consider complementarity between the phasor experiment and the dark matter physics in this scenario. Okay, the last one is the possibility of long-lived U1.
Sorry, Nobuchika, you have 5 minutes left.
Yeah, thank you very much. Okay. All right, so this case, and I consider, and a little bit more extension. This is the B minus model, and or U1X model generally, and I consider this, and they consider the parameter region where the Higgs is long-lived. In this case, and to discuss the symmetry breaking, especially the origin of electric symmetry breaking, and we consider the classically conformal U1 extended standard model. That have been discussed by many people these days, and the last 10 years or so. Okay, so this case, and the very special point is, and the potential has no mass term because the conformal invariance, we impose that. And of course, we cannot justify this the masslessness in the beyond the classical level, but we may think that this theory is something like the massless theory, defined as a massless theory. Okay, just the same way as the original Coleman-Weinberg discussion. All right. So this case, and we have only the quartic coupling for the standard model Higgs doublet and the U1 Higgs, and the quartic mixing coupling. So we take the minus sign here, the conventions, and the lambda mix. I take the lambda mix to be positive. Okay, so so far at 3 level, there is no symmetry breaking. However, the symmetry breaking occurs in the following way. And the first in the symmetry, and the U1 symmetry is broken by radiative collection. So this is just a Coleman-Weinberg mechanism, just the same as the original Coleman-Weinberg discussion. And we have the 3-level coupling and the 1-loop collections, and then we have the balance. If the lambda phi is very small, and the balance with the quantum collections, we have the symmetry breaking. That's the Coleman-Weinberg's way, the Coleman-Weinberg mechanism. Interestingly, once this happens, and we replace this guy roughly to the background expectation value of phi. Then we can generate a negative mass squared for the Higgs doublet. Then we get the electroweak symmetry break, and that's the story. Okay, so we extend this model further. Before that, and this is the Coleman-Weinberg mechanism case, and we have that's a very constrained system. We have the many parameter relations, and the quartic coupling related to the gauge coupling, and so on. Okay, and after that, we get the mass matrix for the standard model Higgs and U1 B minus U1 X Higgs, and then the mixing angle is controlled by the Bible ratio of the standard model Higgs wave divided by U1 Higgs wave. So they are all constrained, and this field is controlled by the mass of this particle and the extra Higgs, and then the mixing angle theta. So this case, if this mass range around this range, and this is the target of the phasor search. Okay, so here actually I consider some more physics, and that's the inflationary universe. I identify the standard model. U1 Higgs, not the standard model Higgs. Okay, U1 Higgs as inflaton. Okay, so this year we already have the inflation scenario discussions today, and so let me skip. And the simplest example is it's in a so-called non-minimal quartic inflation. And this is the same structure as the so-called famous Higgs inflation, standard model Higgs inflation. But here, the inflaton is not the standard model Higgs, that's U1 Higgs. Okay, so we have introduced a non-minimal coupling this way. And quartic coupling dominates during the inflation. This case, and we have the perfect match of the inflationary predictions with a suitable value of non-minimal coupling. Right, so the non-minimal coupling 0 is a textbook lambda phi 4 a chaotic inflation. Switch on the C values and the inflation prediction goes down, and it gets inside the Planck 2018 contour. So this is the perfect scenario. And so the point is any scalar which has the quartic coupling with a suitable choice of C, and the any scalar can be inflaton in this case. Here we discussed and identify the U1 Higgs as the inflaton. Okay, so in this way we have the Kolmar-Weinberg system, and they identify these inflatons, and we actually consider and the connection among the phasor search region and the inflationary prediction, and also the Z prime boson search at LHC. Okay, phasor search is the region, the mass of phi and the theta mixing angle. Inflationary prediction, the C is fixed, everything is fixed, and the M phi and theta fixed, and the C is fixed, and so we have the relation, okay, between the phasor search reach and inflationary prediction. The same way, and the Z prime boson resonance search and is controlled by the gauge coupling and the Z prime boson mass. They are also the function of this parameter in this model. So in this way, that's the result. And this is the phasor search reach, and the green shaded region, the phasor 1, phasor 2 search reach for the standard model singlet scalar M phi, and with the mixing angle theta. Shaded region is already excluded. But actually in this model, in the U1 extended the model, and by identifying the U1 Higgs as the inflaton, and we have the theory implications. Okay, this along this line, for example, and the tensor to scalar ratio is fixed to be the 0.01. So along this line, the tensor to scalar ratio prediction is 0.01. And the almost perpendicular. And once we fix the Z prime boson mass, and along this line, and the Z prime boson mass is fixed. So the best case scenario, if the phasor discover this particle at this point, and we can say something about the what is the tensor to scalar ratio, what is the Z prime boson mass. So that means that once if the best case scenario, if the phasor discover these particles and fixing we can fix the theta and the M phi value, and we have we can cross check this scenario by looking at the future CMB measurement, and also the Z prime boson resonance search at LHC. So this is the scenario. Okay, this summary, and excuse me, and I discussed the U1 extended standard model. So this is a very well motivated the new physics models for the neutrino mass generation or dark matters and also inflation. And depending on the model parameter choice, and all new particles, the heavy neutrino, Z prime boson, and the U1 Higgs, and they can be long-lived. In the U1 Higgs, in this case, I identify this U1 Higgs boson as an inflaton. In this way, we have for each cases, and we can discuss the future search of this long-lived particle to test this scenario. Okay, thank you very much.
Thank you very much for this interesting talk and interesting models. Questions?
Maybe I have one.
Yes.
U1 di Manusel, do you have any hierarchy in the masses of the three particles, connected, so Z prime?
Oh yeah. So that's that depends on the which region is interesting, and I focus on this case, for example, and the mass range of the B minus Higgs is around 1 GeV. Okay.
Yes, but among Z prime, phi, and heavy leptons, do you have a hierarchy?
So the potentially
completely free.
No, they're completely free actually. And Kolmar-Weinberg case, we have the relation between the mass of the Higgs and the mass of Z prime. But the general B minus L model, and they are all free because of the Babe is free, and the gauge boson mass is gauge coupling times Babe, right? So that's free. And the Higgs boson mass is a general case, and the Quartic coupling of the Higgs potential is free. So the M phi is a Quartic square root of Quartic coupling times Babe. That's free. Then the heavy neutrino mass is a Yukawa coupling is free, and so times Babe all free. So but there's some important symmetries like classical conformal invariance. We have some constraint, and we have some relation between them. So without that, and all free actually.
Because this means that you have impact on the phenomenology also of the example of the leptons decays, because if you open up new channels, clearly lifetime can change.
Yeah. Yeah, yeah, yeah. So some limited region, but we can search for these particles. Yeah, normally, Z prime boson is we expect the resonance production of these particles. But the previous case and the FASER search, and if the gauge coupling is very small and the mass of Z prime and the small, actually we can also consider and the long-lived Z prime boson search by experiment. So that all depends on the parameter choice. So far, there's theoretically, and we don't have any predictions, and unfortunately.
Thank you.
Mark, have a question?
Yep.
Marco?
Yeah. So you mentioned inflation and dark matter and neutrino masses, but you didn't mention leptogenesis or baryogenesis.
Oh, yeah,
Maybe I missed it.
Yeah. This may yeah. Well, this depends on the value. Yeah, if we can implement the baryogenesis and this case the leptogenesis, and then discuss and combine this idea to this one, and it will be interesting. But so for example, this scenario, for example, and you can see that the gauge coupling. You can look at the gauge coupling and also the B-minor cell gauge boson mass, and we can get the value, the scale of the BEV, right? B-minor cell symmetry breaking BEV. So this case, we may consider that the heavy neutrino mass, and that such assuming that the Majorana-Yukawa coupling is order 1. So this case, you can calculate this, and some parameter range, and you can see, and the heavy neutrino mass is a kind of intermediate. So this case, we may apply the standard and the summer leptogenesis. However, and so that's quite difficult to connect this to the low energy physics. But with some parameter choice, and I have the successful summer leptogenesis. That is.
Thank you. Dima?
Okay, thanks a lot.
Can you show slide number 13?
13. Let's see. Here.
Yeah. When you discussed this particle and its lifetime, you mentioned that there is a range, which it depends on in this case the mass of the lightest. It's related to the mass of the lightest sterile neutrino.
Yeah.
Where it says the lifetime is that the Matusla have a good prospects to search for this particle. But still, this particle, is produced at the collision point at LHC, and so still we have the LHC detector.
I missed to mention.
Yeah. So there is a part of decays which happens inside the LHC. So still, LHC will be able to cover some whether Matusla is better. Given the geometrical factor, or I just wonder.
I agree with you. Yes. It can still do something, of course. Yeah. So some part of even the mean lifetime is long, but some particle can decay inside the detector. So yeah, thank you very much for the comments. Yeah.
Do we have any other questions? Well, if not,
all right. Thank you very much.
We finish the session. Yes, thanks Nobuchika for the talk.
Thank you very much.
And thank you to all the speakers at the session.